So this video marks the start of chapter 10 of our course. And for the last three chapters, chapter 7, chapter 8, and chapter 9, we've been dealing with two styles of problems. We have P problems, proportion, that we use on categorical variables, and we have mu problems, our average or mean, and we do that on quantitative data. Chapter 10 is the fourth and final unit in this little P mu section of our course. Now, the big difference going on in chapter 10, the one thing that really sets this aside from all the other stuff we were doing in the previous three, instead of just having one group that we're looking at, we're going to end up having two separate groups that we're comparing to one another. So in chapter 7, we learned about sampling distributions. We had one single P that we were looking at, or one single mu, and we built a sampling distribution to estimate it. We learned about confidence intervals. You had one proportion or one mean you were trying to estimate. Same thing with significance testing. We're going to hit all three of those concepts again. Sampling distribution, confidence interval, significance test. But now we're going to end up having two groups instead of just one. That's the key difference that we're looking at when we get into chapter 10. When would you actually use those kind of skills? Why would you need to have two groups instead of just one? The answer is that you will end up using this stuff in chapter 10 all the time. Anytime you want to make a comparison, anytime you want to make comparisons, you're going to end up using chapter 10. Let me explain what I mean by that. Let's say I was getting ready for an election, and I wanted to look at what people thought about some new economic policy. I could just make a single confidence interval, and I could look at that and figure out what percent of people are in favor. Or I could contrast like what Democrats think to what Republicans think, or what male voters think to what female voters think, or what rural versus urban, or I can do all sorts of things where you may want to know how two different groups compare to each other on the same issue. Also, think about experiments, doing any sort of thing where you have a control group versus a treatment group. Control versus treatment is two groups right there that you want to compare to each other. So anytime you're doing a comparison, that's especially true in experiments, you are going to want to do a chapter 10 style question. In this lesson today, we're taking a little bit of a condensed approach to Unit 10. We're going to focus on P problems, and we're going to learn several things about P, all kind of in one bundle here. The first thing we're going to do is talk about confidence intervals in this video, and the next video we'll do significance testing for P as well. So we're focusing here about two proportions specifically. We'll get to mu in later videos. And when we compare two different proportions, usually we would just have a P. That was a proportion symbol. You can go a couple different ways when you have two groups. The most common by far is just to do a P1 and a P2. First proportion, second proportion. You could also do something like, let's say you had men and you had women, or you had like Democrats and you had Republicans. You can feel free to do a subscript that's a letter or a word related to a specific problem, or you can just keep it simple and go P1, P2. But some sort of subscript is going to distinguish between your two proportions. And then the second part of this, how do we actually compare two different quantities? We've done this several times during AP Stats already, so hopefully this should sound a little familiar. You compare things generally with subtraction. You want to subtract one thing from the other, because then you can tell a positive number means one thing, or a negative number means another. So that's what we're going to end up doing. We're going to end up estimating things like P1 minus P2, or maybe PM minus PW, or stuff like this. This will be the sort of thing we end up tackling in this chapter. So we're going to go with just P1, P2 as our parameters right here. We're going to look first at the sampling distribution of P1 hat minus P2 hats. So this looks more complicated than last chapter, and it is a little bit because you have two different parameters that you're worried about. But the math still ties into what you guys already understand. Remember, when I have just one p, I use p hat, which is approximately normal, and I use p hat to get the job done when I'm looking at what can happen in different samples. So if I have just a p, I would want to use p hats. Well, now I don't just have p, I have two separate p's in my problem. I can call them p1 and p2. Well, p2 is going to have its own sample. So I have p2 hat, I have p1 hat over here. And both of these are going to look approximately normal, assuming conditions are met. We learned that sampling distribution of p hats looks approximately normal as long as large counts and all that stuff works. So our job is going to be to compare these two things, p1, p2, which is going to involve subtracting what we get from our samples. In order to answer this and look at what's going on with p1 hat minus p2 hat, we're going to have to use stuff we've learned in previous units. First of all, we learned back in chapter 6. That was our chapter with the random variables where we like smashing them together and stuff like that. If you take a normal thing and a normal thing and you combine them, your result is still going to be normal. So if I make a new picture for p1 hat minus p2 hat, this guy is also going to be approximately normal, probably a different mean and standard deviation. But the shape should still be normal because that's what p1 and p2 hats are. So the sampling distribution of our difference in sample proportions is going to end up being approximately normal as long as conditions are met. So the disclaimer on that is you have to actually pass large counts. And let's think more about this sampling distribution right here for p1 hat minus p2 hat. The mean of this guy, again, we're thinking back to how chapter 6 stuff worked. Mean was our friend back in chapter 6. It just did what common sense said you should do, which is to take the first mean minus the second mean. Well, the mean for p1 hat's graph is going to be at actual p1. The sampling distribution lines up at the true parameter value. And the mean for this guy is p2. So if I subtract these, the mean of p1 hat minus p2 hat, if I was going to write that with crazy symbols, is going to end up being at whatever p1 minus p2 equals. First mean minus second mean. Okay? Nothing too crazy right there. If I'm trying to compare p1 hat minus p2 hat, I subtract their means. The standard deviation, though, this is going to take more chapter 6 knowledge. You guys might recall back in chapter 6 when we learned about random variables. If I wanted to get the standard deviation of two variables that were subtracted from each other, you had to first square them and make them into variances. And then you would add the variance together. So the standard deviation for my first guy over here, this standard deviation was like a little formula. It was square root. It was p times 1 minus p. I'm going to go p1, 1 minus p1 over n, and I'm going to put a 1 on the n as well, because it might be a different sample size for my second group. So I got to take that guy, and I got to square it. So p1, 1 minus p1 over n1. That guy has to be squared to make it a variance. And even though I'm subtracting, remember, you're supposed to add the variances together. I would do the same sort of thing for my second guy over here. I would do square roots, p2 this time, 1 minus p2 over n2, and I would square that. Now those are both going to be variances, so at the end of the day, I would just take a square root of all of that after I add it. And when I do that, I'm going to actually end up getting what you see written right here. The little square roots on the inside, so I'm talking specifically about this guy, is going to cancel with this squared, and the same thing's going to happen over here. Square root and squared cancel each other out. So you're still going to have this big square root on it, but then you just have essentially those little fractions. That was going to be kind of a long way of explaining where the formulas come from. So you guys can actually see it's not just magic what's going on. Your standard deviation is a little more complicated looking because there are two different variables in the problem, but the core is still the same as what we learned in earlier chapters. So the center is going to be at P1 minus P2, and the spread is going to be the formula that you see written down to the right. So if you don't really want to write it again, you certainly don't have to. But it ends up looking like this, all under 1 square root. And hopefully, using chapter 6, you guys are sort of able to see what I did to get that formula written right there. So, key takeaways in terms of sampling distributions when you're subtracting two proportions. Still going to be approximately normal, because if you start out with normal things and you mash them together, the result is still normal. You have a mean and you have a standard deviation based on what's on the slide right there. And from there, guys, you're just doing normal CDF stuff, just like you were in previous chapters. So let's learn how this applies to confidence intervals specifically. Remember, in general, when you write down a confidence interval, you start out with whatever you got from your sample, which we either call a point estimate, or more specifically, it's our statistic for the problem. Confidence intervals start out with a statistic plus or minus that margin of error, which was composed of two pieces. You have, first of all, your critical value. And secondly, you multiply that by either the standard deviation, ideally, or the standard error, more reasonably, if you don't know your true value and stuff like that. Standard deviation and or standard error of statistic. And more often than not, we do end up using p-hats, so then we're obviously going to be using the standard error. So if I just plug in the pieces based on what I did on this last page right here with my picture, to make a confidence interval, I'm going to start with my statistic. That's what I got from my sample. I just took, for my statistic, my first proportion minus my second proportion from my two samples. Looks weird, but that's just what my statistic is, the subtracted difference between my groups. Plus or minus. Critical value. It's still a normal distribution, just with a different standard deviation going on. So I'm still going to use a z star critical value here. Z is for the normal curve. And I'm going to multiply it by that guy that we wrote down on the last page. Now, if I leave these as regular P1s and P2s, well, then I've got myself the standard deviation for my statistic, my sampling distribution. But you guys should know by now, we're not going to actually know P1. That's what we're trying to estimate. And we're not going to know P2 either. So those are going to have hats, and now we're looking at standard error. So the formula makes sense if you just sort of walk your way through it. In this chapter, though, in chapter 10, I'm going to often tell you guys, just go with the calculator and technology to get your interval. While you could plug into this right here, the more pieces there are, the easier it is to screw up and type something in wrong. So it's just better in general to use your calculator for these. There are going to be 3 conditions that we're setting up for doing our little confidence intervals, and they should look familiar. They're a little more annoying to set up truthfully because we've got 2 variables to worry about instead of just 1. But the first thing going on is going to be our random condition. So we need to have, either a random sample, or it needs to be random assignments if we're doing experiments. And then going along with that condition there, not only do we need to have a random sample, like a little new piece that we're tossing in there, since we have 2 variables, our variables need to be independent of one another. That's especially true if we're doing a random sample. So it's important, and you'll see that when we actually go through problems, that taking my sample and like whatever's going on with my first variable can't directly influence what's going on with the second variable. And I'll talk more about that one later. You still need to check your 10% condition, but when you check that 10% condition, you need to check it for both variables. So your first sample size, N1, needs to be less than 10% of the population for the first group. And then you also have your second group, N2, little n2, that has to also be less than 10% of your second population. So my Republican sample needs to be less than 10% of all Republicans. My Democrat sample needs to be less than 10% of all Democrats. You have to do two of them when you're setting it up, but it's not that much harder to write it down. Third and final condition is going to end up relating to the normality. And for that, we're checking our large counts, if you guys recall, back from when we learned about P problems. But if we're doing large counts on a problem like this, instead of just NP, N1 minus P, you're going to have to do that for N1 and N2. So there are actually 4 things in all. Remember, you would end up using P hats for this because you won't know actual P. You need this guy to be greater than or equal to 10. You need N1, 1 minus P1 hats to be greater than or equal to 10. You're also going to check N2 for your second group as well. So there are going to be more pieces to evaluate when you do these. Oops, that should be a 1 minus P2. And then that's going to basically be your setup right there. You've got more pieces to deal with, but it works essentially the same way. My light went off, so I'll be right back. All right, so there's my conditions that I've got set up right there. I'm using significance testing in a separate video, so we'll come back to that later on. I want to jump in and do 2 things with you here. At the bottom of this page where I talk about calculator commands, let me show you guys real fast which command you'll be using for this lesson on confidence intervals. You already know that when we're doing problems, so we're stat test right here, when we're doing problems with just P, a single P, we had the 1 prop Z ints, and we had the 1 prop Z tests. So logically now, I don't just have a P, I have a P1 and a P2. I would be doing either a 2 prop Z test, which we'll learn about next video, or in my situation right here, I'm doing a 2 prop Z interval. So our command that I'm going to write down in this video is going to be choice B, which is a 2 prop Z interval. And we'll see how that actually works in practice when we do our example. So let's look at our big example problem here. We're looking at a survey, and we have independent random samples of men and women here, and we're looking at how much they value job security. So they looked at a random sample of 806 women, and then they looked at a random sample of 944 men. And they looked at the percent of women and the percent of men who said that yes, job security is very or extremely important. Now here's the thing, just to wrap your head around what's going on in this unit. You could make an interval where you're just like, hey, I want to do women, make their interval, I want to do men, make their interval, and just look at them separately. Quick hypothetical here, let's say I did that. Let's say I made an interval for women and it went from, I don't know, 0.62 to, I'm totally making this up, this doesn't relate to the problem. Say it went from like 0.62 to 0.76 for women. And then say I did an interval for men and theirs went from like 0.49 to 0.61 or something like that. Well, I could look at those intervals after I have them separately, and I could be like, hey, all the values in the interval for women are higher than that for men. So probably I have convincing evidence that the women value job security more. That would be a totally fine way of analyzing the problem. Instead of going about it that way, what we're going to do is make an interval, not 2 separate ones. That's chapter 7, chapter 8, chapter 9 stuff. We're going to analyze how far apart those 2 groups actually are. So instead of saying, oh, are women higher? We're going to get a better answer, or a different answer, I should say. And what we're going to look at here is how much higher is one group than the other. So if we did this, we're going to get an answer that looks different than these separate intervals. I might end up getting something like negative 0.05 to positive 0.12. Again, I'm just making things up right now before we jump into our problem. This would mean when you do these problems, you have to know what direction you're subtracting in. Let's say it was women minus men, so P of W minus P of M, like that. This would mean that women are actually 5% lower. So they value job security 5% less, 5 percentage points less, or it could be anywhere from 5 less to 12 percentage points more. So when you analyze the difference, you get slightly different information. If I just see this, I wouldn't know what percent of women and what percent of men. I would only know that women are X percent higher or lower. So you get different information when you do it this way. So I'm going to erase this because this doesn't relate to the problem itself. It would be a good idea, if you want to try to set up this problem yourself, that would be super, just to try to take a look at it and see what's going on. I actually have the answer written out to save a little bit of time in this video, and I want to just walk you guys through all the different steps, give you like a little play-by-play right here. So the first thing you're going to do, it's still a 4-step process, like you guys are used to back in chapter 7, 8, 9. First thing you do is you declare you're setting up an interval. We want a 95% confidence interval, and we're trying to estimate the difference in our two proportions. I chose to do PW and PM for my problem right here. When you mention P1, P2, PW, PM, you always need to define your variables. So you'll see I defined right here, PW is the true proportion of women who say blah, blah, blah. Same thing for men. On my quizzes and tests, I am fine because these look almost identical. If you just do like a little line like this for the rest of it, so you don't have to write the exact same thing again. On the day of the AP test, please just write it out twice. Just be safe when you're doing that. I don't think they'd take off, but just write the whole thing out. So you define your variables and you establish the type of interval or the level of the interval. You need to also specify the direction you're going to subtract. You can do it either way. I picked W first because that's the first thing the problem said. You could reverse it. It doesn't matter. I usually say go in the order the problem says. So we're trying to make an interval. Well, we would need to check our conditions right here. First of all, our samples need to be independent of each other. Let's say I did a random sample and I ended up talking to women and their husbands. Well, women and their husbands are probably in similar financial positions where if the wife is like concerned about job security, probably that her husband is also going to be as well. So that would be a bad way to conduct my sample right here. These would need to be entirely separate groups of, okay, I got my 800 something women, I got my 800, 900 something men. They cannot be related to each other in any fashion. So we have an independent, we just basically say, yeah, it's independent random samples. That condition is pretty easy to check. You'll see that I did the sample size for women and the sample size for men. And I said that each group is less than 10% of the respective population. So you just need to check 2 10% things instead of 1. And when I go to do my large counts right here, you're seeing that I put 4 of them here. We've got 2 that are set up for the women. I opted to use the fractions and leave them that way for my samples. You could easily turn those to decimals and do n times p that way. I don't recommend putting the symbols n1, p1, hat, and so on, because you might put a hat where you're not supposed to or forget a hat and lose credit. So notice that I just went straight to plugging in the numbers. And at the end of the day, I didn't get fancy and say the sampling distribution of p1 hat minus p2 hat. I just checked my 4, all greater than or equal to 10, and said, okay, yeah, the distribution, I just said approximately normal. You could say the distribution is approximately normal if you'd like. So our conditions are verified. We're good to actually conduct an interval right here. You can do it with the formula. This is just a plug and chug style thing using what I gave you guys on the other slide. Or you can opt to do it with technology. And I'm going to show you the technology way just to make sure you've seen it live, not live, but seen me go through the buttons. I showed you earlier we were going to be doing a 2 prop z interval, which is choice B. When you do this, it's going to ask you to feed it the four values, two fractions from this problem. My first group was women. X1, 709 women said yes, out of 806. And for my second group, the men, 802 out of 944. Remember, you can never have a decimal when you type into these here. If they give you a percentage where you convert it and it's a decimal, round it to a whole number when you type these in. We do want a 95% confidence level. You should calculate. And when you do it, you only need to copy down, or you need to copy down for full credit, the name of the test, 2 prob z ints, and the interval that it generates for you, which you can see is written right here. So before we actually talk about our interpretation, let's just conceptually think about what this means. Women were first. It was women minus men. If we get a negative answer, that means women were a little bit smaller in their response than the men were. So women could be like 0.1%, not even 1% lower than men. Or they could be as much as 6%, 6 percentage points higher than men in their valuing of job security. So that is what you can kind of take away from that. How many percentage points higher or lower is one group than the other? So we're going to turn that into our little script for our conclusion like you guys are used to. We are 95% confident that the interval from here to here captures the true difference in proportion. When you write your interpretation, make sure when you talk about the difference, you specify again the direction of the difference. So it was women minus men for this problem. So that's going to be our little interpretation for our conclusion right there. The problem also asked us at the end, is this convincing evidence of a difference in the value of job security? The key with this kind of problem, like we've referenced before, you're going to look to see if 0 is inside that interval. 0 is in this interval because there are negatives and positives in it. That means, in theory, they could be the same value. If you subtract something minus itself, you do get 0. So because 0 is inside of this interval, we can't have convincing evidence. We don't have convincing evidence that there is a difference between the two groups. Let's say they were all positive, and we're really close to all positive here. But if this was a positive number, for example, then we would say we have convincing evidence that women are higher or value job security more. But if that 0 is in the interval, you kind of have an inconclusive situation. So that's how you would handle a confidence interval on a proportion. Next video, we'll go ahead and look instead at significance testing.